Hello, my name is David Hardin from Collins Aerospace, and thank you for attending our talk on formal synthesis of filter components for use in security-enhancing architectural transformations. This is joint work with my colleague Konrad Slind, with additional contributions by Matthew Weiss and Robbie at Kansas State University. Note that the views expressed are those of the authors and do not reflect the official policy or position of the Defense Advanced Research Projects Agency or the U.S. government. The goal of the DARPA Cyber Assured Systems Engineering Program is to develop the necessary design, analysis, and verification tools to allow systems engineers to design in cyber resiliency. Architectural models in the DARPA CASE program are expressed using the Architectural Analysis and Design Language, or AADL. The CASE Cyber Requirements tools examine the AADL models for a given system, identifying potential vulnerabilities. The CASE user then identifies security-enhancing architectural transformations to be applied to the model to address the identified vulnerabilities. Let's say the need for an input well-formedness filter is identified. The CASE user adds the filter to the model and specifies the high-level filter behavior, for example, using a regular expression. The CASE tools then automatically synthesize the filter and produce a proof of filter correctness all the way down to the binary level. The filter is then hosted on a high-integrity operating system, for example, SEL4. Here's a simple UAV use case in which a filter has been placed between the radio component, which talks to the outside world, and the flight planning componentry of the UAV. This well-formedness check ensures that no malformed messages get through to the flight planner. We concur with the LangSec tenet that the only path to trustworthy software that takes untrusted inputs is treating all valid or expected inputs as a formal language. Our work differs somewhat from many LangSec efforts in that we focus on providing standalone high-assurance message filter and monitor components rather than integrating these parsing components into the application themselves. This is due to the fact that part of our mission statement on DARPA CASE is to provide security-enhancing components for existing systems whose legacy components may not be readily modified to introduce a LangSec parser as part of its codebase. We have investigated 3 different formal method specification synthesis approaches on DARPA CASE: regular expressions, context-free grammars, and contiguity types. We will examine each of these in turn. First, regular expressions. Our AADL models feature assume guarantee contracts expressed in the Agree AADL Annex. We have built a translation of Agree component input contracts to regular expressions and provide proof tools for verifying semantic properties of the generated regular expressions. We call this tool SPLAT, for Semantic Properties for Language and Automata Theory, since it combines formal language theory with specifications on the interpretation of the flat strings comprising the message format. SPLAT also provides automatic synthesis of message handling binary code using the facilities of the KCML verified compiler. In previous work, we had implemented the Brzezowski deterministic finite state automaton compilation technique for regular expressions, and we have performed a correctness proof for regular expression compilation to DFAs, contributing it to the Hall 4 theorem prover distribution, which you can find online. Thus, we can utilize a verified compiler toolchain to create a verified regular expression pattern matcher all the way down to the binary level, using the facilities of the KCML compiler, which is itself implemented in Hall 4. Thus, we produce a very performant, very simple DFA state traversal function implemented in verified fashion. The general flow for the SPLAT tool is as shown in this figure, where an AADL model is mined for the message format regular expression that we're interested in. That regular expression is then compiled to a DFA and then submitted to the back end of the KCML verified compiler for ML, which is itself implemented in Hall 4, producing machine code that is then run on the SEL4 high assurance microkernel. In another approach, we examined using context-free grammars for message specifications. Consider a use case in which a UAV air-ground communication system employs JSON to encode certain messages sent between a ground-based control station and the UAV. For example, a UAV coordinate could be encoded in JSON as shown. In order to create a well-formedness filter for JSON input, we need to perform both lexical and syntactic analysis on any candidate JSON message to ensure that it is in fact legal JSON. We describe the lexemes of JSON by way of regular expressions. JSON lexemes include the various literals of JSON as well as its punctuation characters. A lexical analyzer generator accepts these regular expression token specifications and produces a lexer that takes an input candidate JSON message and produces a list of JSON tokens at its output. We combine the individual regular expressions for our JSON tokens to create the overall DFA table for the lexer. For syntactic analysis, we utilize a verified parser generator to create a verified parser table for JSON. In particular, we utilize the Vermilion verified LL1 parser due to Sam Lasser and colleagues at Tufts University. We present a set of grammar rules for legal JSON messages to Vermilion, extract the verified parser table, then transfer the verified parser table to our target system. By generating both the lexer table and the parse table in formally verified fashion, we enable verified data to be transferred from host-based provers to the target system. The parsing function is a bit more complicated than the lexer in that it requires a rule stack. Otherwise, it also is a fairly straightforward table traverser. Now, let's further assume that we want to create a JSON filter that could be implemented either as hardware or as software. We utilize the verified lexer generator and parser generator capabilities previously described to create the lexer table and parser table for JSON. The table traverser code is then currently written by hand in a hardware-software co-design language, but in the future this code will be automatically generated. And for the parser rule stack, we utilize a previously verified fixed-size stack component written in the same hardware-software co-design language that we will discuss later. The resulting JSON filter, built from hardware-software co-assurance components, is depicted schematically on this slide. The input is first presented to the lexer, which produces a stream of lexemes, which are then passed to the parser. The parser utilizes its rule stack to parse the input tokens and produce filter output, or no output if the input is not legal JSON. Both the lexer table and parser table are generated offline using a verified lexer generator and parser generator as previously described. Thus, we have a transfer of verified data from the build system to the target system, in both hardware and software form. The particular hardware-software verification approach we employ was developed by David Russinoff and John O'Leary when both were at Intel. This was later refined by Russinoff to a system called RAC, or Restricted Algorithmic C, which is extensively documented in Russinoff's 2018 book. RAC and the verifications described in this book are all part of the standard ACL2 theorem prover distribution. Algorithmic C provides a basis for writing bit-accurate algorithms to be synthesized into hardware. For example, one can write a specification in Algorithmic C for a example 112-bit scalar value for use in floating-point hardware data paths. Algorithmic C is supported by Mentor synthesis tools, for example Catapult, and the full specification for Algorithmic C is available online. Russinoff's Restricted Algorithmic C, or RAC, further constrains Algorithmic C to facilitate proof and is well documented in Chapter 15 of Russinoff's book on floating-point hardware verification. Schematically, the Restricted Algorithmic C toolchain looks as follows. The source code uses Algorithmic C headers to provide bit-accurate data types. The source can either be compiled by a C++ compiler, which can be used for pure software implementation or for simulation and test of a hardware-based implementation. Or it can be subjected to hardware design tools for synthesis, simulation, test, equivalence checking, and so on. The RAC source is also submitted to a RAC to ACL2 translator, allowing us to prove theorems about it using the ACL2 theorem prover. The ACL2 theorem prover uses a set of lemma libraries to reason about, for example, modular integers, and produces proofs in the form of certification files that can then be reused in larger system proof attempts. In order to perform a proof of concept for synthesizing hardware directly from AADL models, colleagues at Kansas State University have taken a simple AADL model that includes a filter of the form we've been discussing, written in a hardware-software co-design language, and then synthesized an implementation targeting an FPGA development board. In this proof of concept example, the filter, which is implemented in FPGA gates, is fed by a Linux process running on an embedded microprocessor within the FPGA chip. The output from the filter is received by another Linux process also running on the embedded microprocessor within the FPGA chip. Thus, we can, by examining the console output of the input and output processes, determine whether the filter is doing its job. This slide provides a photo of the FPGA development board. It's a very inexpensive Z board for Xilinx FPGAs. You can also see the consoles for the producer and consumer processes that feed and then monitor the filter. And you can see that certain messages presented to the filter are accepted and others are rejected dependent on their well-formedness. Finally, I'd like to spend some time talking about a novel message specification system we've been developing called contiguity types. Contiguity types were developed to deal with so-called self-describing message formats. A self-describing message format, for example, would be one where early in the message there's a link field which tells you how many bytes there are in the remainder of the message. These self-describing message formats are at odds with standard lexer and parser technology. Regular languages are insufficient, and context-free grammars can't capture the dependency of one field on another that characterizes self-describing message formats. Context-sensitive grammars are a possible approach, but there's little tool support for these. Parser combinators could be used as well as dependent type approaches. However, we've decided to take a formal language theory approach since there's a strong connection between messages, that is, flat strings of bits or bytes, and the strings of formal language theory. Contiguity types attempt to bridge the gap between standard data structures, base types, arrays, records, and formal language theory. We start with a collection of base types. The array construct uses arithmetic expressions to describe the number of elements in the array. The union construct uses Boolean expressions to decide which choice to take amongst the alternatives offered. In both cases, expressions can refer to earlier elements in the message. L values and R values provide a comprehensive notation for such references. L values can occur on the left side of an assignment and R values on the right side. Some example contiguity types here presented include a simple record, an array of a specific length, a two-dimensional array, and also two versions of a GPS coordinate message selected by a release field. If the release is less than or equal to 14, the message format is simply the lat, long, and altitude. If the release is greater than 14, then there's additional information in the record. This is captured succinctly by the union primitive. We can also have assertions on contiguity type messages. Assertions are of the form, if some Boolean expression is true, continue without consuming any bytes, otherwise fail. We can place assertion inside contiguity types that will be checked when the message handler runs. So, for example, for a variable length array with a particular bound, we can include an assertion that checks that the length of the array, as provided as a field in the contiguity type, is indeed less than the bound. We've developed several algorithms for dealing with contiguity types, including decoding, filtering, serialization, test generation, and learning, and we have implemented decoding, filtering, and test generation capabilities to date. Contiguity types look like normal programming language types, but they are in fact formal languages. Each base type is characterized by its width and denotes all byte strings of that width. Thus, the meaning of base type I64 is all strings of width 8 bytes. The meaning of a record having fields f1 of type tau1 through fn of type tau-n is the concatenation of the languages denoted by tau1 through tau-n. The meaning of array is evaluate expression exp to get a natural number in. The result is then the in-array concatenation of the language denoted by tau. The meaning of union is that if there is exactly one binary expression that evaluates to true, return the language denoted by tau k, else return the empty language. Expression evaluation is done with respect to an environment that maps L values to slices of the message. We have defined contiguity types and matcher and filter functions over them in the Hall 4 theorem prover. These have been proved to terminate. Match attempts to match the contiguity type against the byte array. If successful, match returns a built-up environment which binds locations specified by tau to segments of the byte array. This leads to a very straightforward statement of the formal correctness of the match function. We also need a theorem relating the language of a contiguity type with matcher behavior as depicted on this slide. For more details, see Konrad Slind's paper at the 2021 Interactive Theorem Proving Conference. In conclusion, we have detailed a method and toolchain for the creation of formally verified critical system components developed for the DARPA CASE program. We have demonstrated how this toolchain can be used to implement security-enhancing transformations on system architectures specified in AADL, with implementations automatically synthesized using the verified KCML compiler. We have described the use of regular expressions, context-free languages, and a novel contiguity type specification language to formally describe message formats. We have conducted formal synthesis for well-formedness checkers, including verified DFA generation, table-driven lexer generation, and table-driven parser generation. We've also described methods and tools for enhancing the safety and security of critical systems using a hardware-software co-design and co-assurance approach. In future work, we will continue to enhance our verified synthesis tools for increasingly complex systems, including those provided by our product area partners. We will continue to evolve the contiguity type specification language, developing a compiler for contiguity type specifications, and bridging the gap with conventional parsing technology based on context-free grammars. Thank you for your time and attention.